Alright, on Friday we talked about matter and the classifications of matter as far as changes and properties and physical properties and chemical properties. So today we need to finish up section 2 of chapter 1, talking about how matter is classified. Remember that an element is matter that is composed of one kind of atom, and all the atoms have the same properties, and they can't be separated into different kinds of atoms, whereas a compound is a combination of different kinds of elements that come together to form a compound, which is multiple types of atoms together. So let's talk about the classification of matter. First question is, well, if it's matter, then we want to know, can it be separated? If it can be separated, if the answer is yes, it can be separated, then we call that matter a mixture. A mixture is matter that can be separated into different kinds of elements. So, a mixture is a blend of two or more kinds of matter, each retaining its own identity and properties. There are two types of mixtures. You have homogeneous mixtures or homogeneous mixtures. Homogeneous mixtures are uniform in composition, meaning that they are the same throughout the solution. So that's a solution. Homo, the word homo in Latin means the same. Therefore, homogeneous mixtures or homogeneous mixtures are mixtures that no matter what part of the mixture you take, it's all the same. It's the same kinds of atoms, the same things that are making up the mixture. The opposite of a homogeneous mixture is a heterogeneous mixture. Hetero in Latin means different or other, and so heterogeneous mixtures are not uniform throughout. You can usually separate these. So heterogeneous mixtures, a lot of times the heavier particles will separate out of them, and in order to get the mixture back together, you have to shake it up or stir it up. So if we were looking at like things that you drink, milk is a homogeneous mixture, and they even say homogenized milk on the side of the milk carton. It's a mixture that no matter where you take it from, if you take it from the top of the milk container or the bottom of the milk container, the solution is going to be all the same. Whereas orange juice is a heterogeneous mixture, because orange juice has large particles and smaller things that can separate out. So before you drink your orange juice, you have to mix it up so that it's all mixed together, so that we try to make it a solution, but it never will be a solution because the bigger things will fall out of the heterogeneous mixture. Alright, so moving on. What if the particles, the matter, cannot be separated into different things? If the answer is no, then we call this a pure substance. Alright, so a pure substance is every sample of a pure substance has exactly the same properties. No matter how big or small the sample is, no matter if you're talking about one atom or a ton of that substance, it's all going to act and behave exactly the same way. So, every sample of a pure substance has exactly the same composition. Pure substances can be divided into two kinds, either elements, which is one kind of atom. It can't be decomposed. An example of that is like carbon atoms. An element is just carbon atoms, nothing else in there. Or a pure substance could be a compound. So two or more kinds of atoms, they can be decomposed into its elements. An example of that is water. The formula for water is H2O. H2O can be broken down into hydrogen and oxygen. So we can do a chemical reaction called electrolysis and break down water and make hydrogen gas and oxygen gas, and we would see that in the form of bubbles. Basically, you just electrocute the water. You add electricity to it, and that breaks it down into each of these types of atoms. So water is a compound because it has two kinds of atoms that make up the water molecule. Alright, so elements. What are we talking about when we're talking about elements? Remember, the definition of an element is one kind of atom that all the atoms behave exactly the same way. They have the same properties. All the known elements are placed on the periodic table and organized in two ways. And if you look at the periodic table, there are 92 naturally occurring elements, and then there's a bunch of elements that are man-made elements. So, if you look at the periodic table, we call parts of the periodic table by certain names. So the columns, the ones that run vertically up and down, are called groups or families. There are 18 columns, so if you look across the periodic table, it's labeled 1 through 18, and we call them groups. We're referring to the columns. So group 1 is the first column of a periodic table that starts with hydrogen, that has lithium, sodium, potassium, rubidium, cesium, and francium. That's group 1. Or if you were looking at group 18, that would be your noble gases over all the way on the right-hand side. That would be helium, neon, argon, krypton, xenon, and radon. Those are your groups. So that's called the noble gas group or the alkali earth metal group. Those are your groups. The other way it's organized is by rows. Rows run horizontally. There are 7 rows, and they are called periods. So if we're referring to a certain row, we would refer to period 4. So if we were looking at the periodic table and we were talking about which period is calcium in, well, calcium is element number 20, and it's in the 4th row, which means it's in the 4th period. So the periodic table is arranged in order by their atomic number. You guys should know that from 8th grade physical science, and they go in order by the number of protons that they have. So hydrogen has 1, helium has 2, and then you go to the next row. And because of some of their properties, they end up in columns, and everything in the same column acts the same way. They have the same kind of chemical properties. The rows just help you know things about where they are as far as their electrons and where the electrons are in the structure of the atom. And we'll get to that when we get to chapter 3 or 4. Alright, so types of elements. There are 3 types of elements. The first type of elements are called metals. Metals are left of the stair-step line. So if you look at the periodic table that I have over on the wall, you'll see over on the right-hand side, sort of in the middle of the right-hand side, you'll see the red stair-step that goes between boron and aluminum, silicon and germanium, and all the way down. That's called the stair-step, and that's like an invisible barrier between the two sides of the periodic table. So all the elements on the left side of the stair-step are metals. Well, what makes them metals? Well, this is the definition of a metal. The ability to conduct heat and electricity. That's what defines something as a metal. So if you look at the elements over there, they're metals that you know. So starting over in the middle, you'll see copper, zinc, silver, gold, platinum, nickel, iron, chromium. Those are all metals that you're familiar with. A lot of those metals are metals that we use to make jewelry or coins, and so those are called precious metals or coinage metals. The rest of these you may not think are metals. You think sodium. Sodium is actually a metal. Now when we think of sodium, we don't think of sodium as the element sodium. We tend to think of sodium as, you know, salt, table salt, the white stuff that's on your kitchen table. But sodium, when it's by itself, not in a compound, is a metal. Why is it a metal? Well, because it's a good conductor of heat and electricity. Most of the metals are solid and at room temperature, with one exception, and you'll find that down in period 6, and that would be mercury. Mercury is a liquid at room temperature, and so if you look at my periodic table on the wall, the mercury is blue, and that identifies mercury as being a liquid at room temperature. Everything else is black, and black means it's a solid at room temperature. Other properties of metals is they are malleable, they are ductile, and they have luster. Well, so what does that mean? Malleable means we can hammer them out and make them form different shapes. So think of like a blacksmith. Blacksmith, you've seen, heats up the metal and then hits it with his hammer on the anvil and forces it to become, you know, a nail or a horseshoe, whatever. Ductile means it can be pulled out and become a wire. And then luster means it's shiny. So we like those silver, gold, platinum things because they're nice and shiny and, well, they have bling. So that's the characteristics of a metal. So know that the definition of a metal is the ability to conduct heat and electricity. And then metals have the following properties. They're solids. Most of them are solids at room temperature. They're malleable, they're ductile, and they have luster. So if it's not a metal, then what is it? Well, then it's a nonmetal. So to the right of the stair step, all the properties, all those elements are called nonmetals. All the properties are of opposite of metals. So what do we know about them? Well, they are not good conductors of heat and electricity. They are not malleable. They are not ductile. They do not have luster. Most of them, if they are solid, are brittle solids. So think of like a charcoal briquette. That's a brittle solid. And so copper is brittle. If we were to hit it with a hammer, it would just shatter into lots of little pieces of charcoal. The rest of the elements, if you look over there, you've got several elements that are red on my periodic table. Those elements are gases at room temperature. So you see nitrogen, oxygen, fluorine, chlorine, and then your noble gases. Those are all gases at room temperature. So they're not good conductors of electricity. We can't hammer them, we can't make them into wires, and they're not shiny. Why? Because, well, they're gases. You also have one nonmetal that is a liquid at room temperature, and that's bromine. And you see on my periodic table on the wall, bromine is blue. So that tells you that that one is a liquid at room temperature. So there's one group that falls right along the stair step. They are called metalloids. Metalloids don't fit in the other two groups, meaning they might be hard, solid, but not good conductors of heat or electricity. Or they actually might be a brittle solid, but be a good conductor of heat and electricity. So they tend to have properties of both metals and nonmetals, and they tend to act like the side that they're on. So when you look at them, you can kind of predict some of their properties based on what side that they're on. All right, so looking at the periodic table, well, what are our metalloids? Well, the metalloids are the ones that are touching the stair steps with a couple of exceptions, okay? And another name for this are semiconductors, and we see them a lot used in the electronics industry. So silicon, that's a metalloid. Boron is a metalloid, so up there in period 2, the B element, boron, that's a metalloid. Silicon is a metalloid in period 3. In period 4, you have germanium and arsenic, so Ge and As, those are metalloids. In period 5, you have antimony, which is symbol is Sb, and tellurium, which is Te, those are also metalloids. So you see that those are touching the stair step, and so those ones are the metalloids. So there are two exceptions of things that are touching the stair step that aren't metalloids. Number 13, Al, that's aluminum. That's a metal, you know that. And then number 84, Po, polonium, that's also a metal. So they notice that they're on the metal side of the stair step. They are definitely metals. So really you just have a couple of metalloids, and just know that they don't have exactly the properties of metals or nonmetals. They kind of fall in that gray area. So the ones right along the stair step are the gray area elements. Alright, so states of matter of your elements. At room temperature, the state of matter can be determined by the color of the element symbol on the periodic table. So if the element symbol is black, it's a solid. If the element symbol is blue, it's a liquid. And notice there's only two. Mercury, Hg, number 80, that's a metal. And bromine, number 35, Br, that's a nonmetal. And both of those are liquids at room temperature. If it's red, then it's a gas. And all of your gases are nonmetals with the exception of hydrogen. Now, hydrogen isn't necessarily a metal. We put hydrogen over there because it acts and behaves like all the other group 1 elements. But keep in mind, hydrogen is not a metal. It's kind of its own category because of the things that it can do. Now, on my periodic table, you'll see that there are some elements that are clear. They're not colored in. There's one right in the middle, number 43, technetium. And then down at the bottom, all along the bottom, you see a bunch of elements, number 61, and then number 93 through 103. All of those elements are man-made elements, and they're radioactive, and they tend not to stay around for very long, and some of them we don't know a whole lot about because they were created in a lab by people like Tony Stark that have particle accelerators and like to make elements in their spare time. So those are your man-made elements. So if you see an element on my periodic table that's clear, that means it's a man-made element. Alright, so getting away from the elements for a minute, and we're going to talk about scientific notation. This is technically a math concept, but I wanted to go over it to make sure we refresh it in your minds because we're going to be using numbers in scientific notation. Alright, so what is scientific notation? It's a way to show a very large number or a very small number without all those placeholders or zeros. So numbers that are really, really big that have lots and lots of zeros, or numbers that are really, 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 really small that have lots and lots of zeros, we can shorten it up and make it easier to write those numbers without having to write all those zeros, because sometimes we lose the zeros and that will mess up our math. So, for example, here's a number, 620014129270000000000. Lots of zeros. That is not fun to write out every time you use it. So to shorten it up, we put it in scientific notation, 6.022 times 10 to the 23. That is the same number, but in scientific notation. Basically, we've taken out all of these zeros, and we've taken everything out and noted it up to this point. Another one, for a really small number, 0.0000000000235154. That's a lot of zeros. We don't want to lose our zeros, so we can change it to scientific notation, making it 2.3154 times 10 to the negative 11. All right. So notice the really, really big number, we're taking out all of these tens places, and it has a positive exponent. The really small number, we're also taking out all of these tens places, but these are like fractions, and so our exponent has a negative number here. So, what is the proper form for scientific notation? Well, first, you have one whole number in the front before the decimal. Then all the rest of the non-zero digits are placed after the decimal. They're called significant digits. We're going to learn more about those later, but I want you to start getting used to that. All right, the exponent of the 10 is equal to the number of places the decimal is moved. Remember that a positive exponent means the number is greater than 10, and a negative exponent means the number is less than 1. It's a small decimal type number. All right, so let's look at a couple of examples. So here we have 643,201. So 643,201. That's a really, really big number. So what we want to do is we want to make that number into scientific notation. So here's what we're going to do. Where is the decimal to start with? Well, if you look, it has no decimal here, so we would say the decimal would be right there. All right. Now, we're going to move this decimal to the proper place, which is right after one whole number. We're going to move it to this spot right here. And so all we have to do is count how many places we're going to move it. So we're going to move it 1, 2, 3, 4, 5 places. And so that makes my number 6.4321 times 10 to the 5, because we moved this. Essentially, we took out 100,000, and that's what this number represents. That represents the 100,000 that we took out of there. All right, another example. Again, we've got a really, really big number. And so when we look at this number, our decimal is back here at the end of the number. And so we're going to move this number so that the decimal goes right here. And we're going to count how many places we're going to move that number. So we're going to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And so that's 6.02214 times 10 to the 23, which represents how many tens we took out of there by moving that decimal to that place. All right, so those were two really, really big numbers. So let's look at some small numbers. So here's a small number, 0.0023, and we want to move the decimal. So we have one whole number. So we're going to move the decimal to in between the 2 and the 3. And how are we going to move it? Well, we're going to move it 1, 2, 3 places, and we moved it this way. So we took 3 out, and that makes it 10 to the negative 3, because this is a small number, and small numbers have negative exponents for their 10. All right, another one. Really small number. We don't have to write that number all the time because there's a lot of zeros in there, and I tend to lose my zeros when I do math. So instead, I'm going to make it easier, and I'm going to make this a decimal number. And so, a scientific notation number. And so I want to move my decimal to be right here between the 2 and the 3. So I just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so this is 2.3154 times 10 to the negative 11, because I moved it 11 places in this direction. So keep that in mind. Big numbers have positive 10s, and little numbers have negative 10s. So today you're going to do the worksheets on classification of matter, physical and chemical properties, and then a quick practice with scientific notation, converting between the scientific notation and the regular notation. Don't forget that on Wednesday you're going to have an element quiz, so I would suggest that you make some flashcards for Group 1, Group 2, and the noble gases, which is Group 18. Make sure you're comfortable with those. You need to know just the symbol and the name of the element so that you're comfortable with that. I'm not going to make you memorize the numbers. I just want you to know what's the symbol for sodium. And so you would say, well, the symbol for sodium is Na. Or what does Ne represent? Well, that would be neon. Neon is in group 18. So you need to know the elements and their symbols. And additionally, I want you to know the elements in group 18 in order. So make sure you learn that it goes helium, neon, argon, krypton, xenon, radon, in that order. And that will help you guys out with your quiz, which is going to be on Wednesday. Make sure that you have signed up for Edmodo, because your lab safety quiz is on Edmodo, and you need to get that done today because it's going to close tonight. So make sure that you get on Edmodo. And if you're having any problems with Edmodo, please email me and I can check my emails and make sure that you guys are getting what you need. So good luck. Work on the worksheet. It's due tomorrow, so make sure you have all that stuff done before tomorrow. See you guys.